Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. This is Module 6, Backpropagation-Based Training, Part 3, the Atom Update Rule. So the Atom Update Rule, just like we talked about before, classic backpropagation, it's just another way of calculating V to put into this weight update algorithm that we had before. Now the atom update rule, what is very nice about it is it doesn't have, you don't really have to focus too much on a learning rate. There is a learning rate present, but of the values that you have, the authors of the original paper, Kingma and Ba, they give some good recommendations for the hyperparameters, and I rarely, even that learning rate at the end, 10 to the negative eighth, you often do not have to change those. This is a relatively new training algorithm. It was introduced in 2014. It's a popular one. It deals with training for sparse data where lots of missing values, and then also stochastic error function. The error function is stochastic because we're doing stochastic gradient descent. So we're constantly randomly subsampling a batch size, a mini batch, and updating the neural network based on that. So the changes that you make from one iteration to the other might not help because you're grabbing a different set of training data on each one. The paper for this is given here at at Cornell University, the archive. If you haven't dealt with archive before, that's the Greek letter chi, so archive. It is a place that you can store your academic papers, and many of the authors of these papers do store them here. And what's really nice about it is you have a whole history. So 2014, 2015, you can tell they were pretty active on this paper up through 2014, 2015, and then they updated again in 2017. So rather than having your paper stuck not in a bound printed academic journal stuck somewhere in the library at this university, you can make changes to it as you go. And if you click on the PDF, it will show you the actual paper for this. And if you were looking to implement this from scratch, and I have implemented this in Java. It's not too bad to implement. I implemented it for Incog, but which is a Java package for deep learning that I work on, and not quite as much anymore. I use TensorFlow primarily these days, but this gives you all of the pseudocode here. So this is pseudocode written in sort of mathematical style pseudocode. This is really all you have to implement to actually make it happen. And this is a very typical sort of training algorithm, while theta, so very similar notation to what we have in the class module, while theta for the current time has not converged. That's a very somewhat ambiguous statement. It's implying early stopping. So whatever your criteria for converged is, while that has not happened, continue going through this. So we're going to essentially, this is using something in mathematics or statistics in particular called moment estimation. And moment estimation, method of moments that you see here, it's a way of estimating each of the moments of a distribution of values. So that's the mean, the variance, and so on. So let's look at the actual paper for this. This is very similar to the code that we've seen for the other ones. So this is just t equals t plus 1. That's indicating that we're moving through the time. We're initializing the first and second moments. The first moment is the mean, so the mean of the gradients that you're trying to estimate. And v is the variance, so the second moment. There is a third and additional moments, but all we're dealing with are these two, the first two moments. By the way, that's where the name ADAM comes from, adaptive moment estimation. And then we initialize the time set to 0. So these two initial estimates are 0. We are going to calculate the g, the gradient. So this is the gradient, just like we're doing before. Very similar to classic backpropagation. A little bit different terminology. Instead of the j that I use, they use f. So this is the loss function with the weights. That's exactly the notation from the module for the previous one. And we are going to get that gradient. These two values deal with a bias on that occurs early on. Since these are initialized to 0, that creates a tremendous bias towards 0. So these are just two, I'm sorry, the hats down here are actually that. That's where they're calculating they're dealing with the initial fact that these are starting out at 0. So m hat and v hat. M and vt themselves, this is essentially updating each of these. So you'll notice that it's m based on the previous t. They're updating as they go through it. They are essentially creating more and more of an estimate of the first and second moments. And these are vectors. Obviously, they're across the weights. So that's essentially creating almost a learning rate for each. The first one is on the first power and then second power, so this is squared. We calculate these adjustment values just to deal with the fact that these started at a 0. And then we're going to update the weights. So weight t, this is very simple. So this part is exactly like what we had from trying to highlight the bottom row, but up to here is exactly what we had for the for classic. We're subtracting the gradient, but instead of subtracting the gradient, we're using this formula to update the parameters. Parameters are weights. Alpha is the learning rate. So usually learning rates, or step size as they call it, you're multiplying by the rest of this to scale this. And you're putting in the two hat values, which were based on these, just to adjust them so that they're not so biased initially towards 0. That is essentially ADAM. It's a little bit more complicated than your classic backpropagation, but not a whole lot. I mean, this is not terrible to implement in Java or another programming language. They discuss the algorithm, and they talk about that initial bias correction, why that is needed, and how you are calculating the two hat values that are very necessary for that. I will admit I have not read through this part and find it somewhat very complex. They're doing some analysis of the convergence. This is essentially proof for why it works. And then they quote related work. And then experiments where they sort of empirically prove through experiment why it works. And with the theorems, they attempt to talk about why it, sort of proof-wise, why it works. Related work, RMS-Prop and AdaGrad, those are two other very similar training techniques that existed prior to ADAM. And this is just straight sort of from the paper, but I like looking at the pseudocode a little bit better, but I reproduced it there if you're interested in it. This is a really good diagram. I did not create it. I have links to where this is where I found it. Yeah. So anyway, and then he cites it to the original author. So you can definitely want to give credit where credit is due. This is a very, very good diagram of this. It's an animated GIF. So this is essentially a search space. So you can think of this as a rugged sort of two-dimensional plane. Star is the lowest point. That's where you want to get to, and it's sort of like marbles rolling down a ridge. This is stochastic gradient descent, which is the slowest one. So that's your classic backpropagation. It's eventually getting there. The one that gets there really first is added delta, and it seems like green momentum starts out slow, but then really, as you can see, builds up the momentum and then blasts right past it. So just your different training methods. Atom is not on here because when this was created, atom did not exist, or at least was not all that common yet. But you can definitely see some of them, like momentum. It's very obvious that it starts to really build that momentum, the little green ball, and shoots right past it. SGD is just slowly, methodically working there, and it doesn't even make it. They give up and reset it because everybody else has made it. Keras and TensorFlow has a variety of these techniques available for you. The ones that are highlighted, they have stochastic gradient descent and atom. I believe there's other ways you can get to some of these. I'm sorry, these are all of the ones that TensorFlow has. I honestly have no idea what FTRL is, and I'm familiar with the other ones. The ones that I have highlighted are probably the ones you're the most interested in. I would be tempted to highlight RMS prop as well. You can definitely experiment with these and get potentially better results. Where you specify it is down here with the optimizer. If you specify one of these that means a learning rate, you'll pass in a class here and actually pass in the parameters as well. You can go to the TensorFlow documentation, and they show you, or Keras anyway, and they give you the actual class names for this. But you can just use any of them just by putting its name in here. You'll need to put an object in there if you want to specify even additional parameters. These are some of the results that I got trying these out. So you can see that on the miles per gallon data set, we got basically different results, and some, like you notice, momentum needed a lot more training than, say, atom, showing the last successful or the last number of iterations. So atom converges pretty quick. I'm pretty fond of that training technique, and I use it often. Adagrad is also pretty good as well. So Adagrad I like. RMS prop definitely I have seen it has uses. I will try between these and look at them when I am training neural networks, and I often start with atom, but then we'll try Adagrad or RMS prop. There are probably better, more scientific ways to pick those, but that tends to work pretty well for me. All right, that is the end of this module.